Okay, so the third section of chapter 3 is called the properties of logarithms, and so we'll introduce the properties of logarithms and then use them, apply them. And this is also another important thing for calculus. You have to use the properties of logarithms to solve calculus problems with logarithms, but also there are non-logarithmic solutions that use logarithms in their method to make the problem solvable. So you'll see this again. So the first thing we're going to talk about is the change of base formula. What this does is it allows you to find the logarithm of a value x at a base a if you only have the logarithms for other bases. So typically, back in the old days when we just had books, there was usually a table for logarithms to the base 10 and logarithms to the base e, which are natural logarithms. So, and if you look at your calculator, you'll see that you have log, L-O-G, which is log to the base 10. So if you see on your calculator something that says log, that's of x, that's really log to the base 10 of x. And if you see the natural log of x, that's just the natural log of x. So they don't necessarily show base 10, but they show just say the log. So they have two bases that they have logarithms for. But as you've seen, if you want to find what is log to the base 3 of 7, how do you do that? Using your calculator. Well, some of the fancy calculators will actually allow you to do this directly, but some of them just have these two functions. So you have to use this. And we'll find out later that this one is used not just for finding the logarithms at bases other than e or 10, it's to be able to solve calculus problems. We have to use this change of base formula. So in general, if you have a expression with the base a of some value x, you can find this logarithm by taking any other base b, taking the logarithm to the base b of x and dividing by the logarithm to the base b of a, which is the base for the original logarithm. Now specifically, if you have base 10, b is 10, so you just put 10 in there, or if b is e, then you can use the natural logarithm. So let's, this is a calculator, TI-83 plus, but the ones you have probably very similar. You'll see down here is log, and here's the natural log, and it's the same on mine, which is a TI-84. So this is log to the base 10. This is log to the base e. So let's say you want to find out what is the log of 20 to the base 3. Well, there's two ways of doing it. You can take 20, the log of 20 base 10 and the log 3 base 10. 3 is the base of the original expression. So if you go into your calculator, so pull out your calculator, and what you would do is you would say log log of 20, and that would be 1.30102 with some other stuff. And then if you take log 3, so this one, log of 3, you'll get 0.47712, and if you take that 1.3010 divided by 0.47712, you'll get 2.7268. Okay, so that is the log of 20 to the base 3, and the equivalent exponential thing says that this is your base, so it says 3 to the 2.7268 should equal approximately 20. It's approximately because I've only got five numbers there. So any calculator will do exponential. So let's plug this in. So we take 3, raise it to the 2.7268 power, and what you'll get is 19.9993. And the only reason it's not exactly 20 is because I didn't carry out this to an infinite number of decimal points. And if you remember, 3 squared equals 9, 3 cubed equals 27. So you'd expect the logarithm of 20, which is between 9 and 27, to be somewhere between 2 and 3, which it is. 2.7 is closer to 20 than to 9, so it's not surprising. It's closer to 3 than to 2. You can also do the same thing using the natural log. That's the other thing that's on your calculator. So you take the natural log of 20 divided by the natural log of 3. So the natural log of 20 is 2.99573, and the natural log of 3 is 1.09861. So 2.99573 divided by 1.09861 should be 2.7268. And if you do that, you get 2.7268. Okay, so let's look at another one. So log base 6 of 125. Again, there's two ways. You can use log base 10. So we plug that in, log 125. That's 2.09691. The log base 10 of 6, which is the base of the original expression, is 0.77815. Now we do the division, and you can, do this all in one step in your calculator if you want to. I'm just doing it to show you. And so you get 2.6947. So that's a log of 6. And again, 6 squared is 36. 6 cubed is 196, I think. 6 cubed, 216. So we have 125, which is between 36 and 216. So the log would be somewhere between 2 and 3 again. It is. You can also then use the natural log. That's the other thing that your calculator will do for you. So the natural log of 216 is 5.37528, and the natural log of 6 is 1.79176. 5.37528 divided by 1.79176. Got a different answer. What did I do? Oh, because I put 216 in there. So the natural, that's wrong. Natural log of 125 is 4.8283 divided by 1.79176, and I get 2.6947. Now, so that's change of base formula. This is a picture of slide rule, which you may or may not have seen. And the slide rule was the way that engineers and scientists used to do calculations, approximate calculations, before the invention of the calculator. And the whole point of a slide rule is to multiply or divide two numbers. And it uses the properties of logarithms to do that. So you've got 1, 2, 3, 4, 5, 6, 7, 8, and it would go 9. And the spacing you see is not equal. The spacing is based on the logarithms of 1, 2, 3, 4, 5, 6, 7. So what you do when you use a slide rule, you add logarithms together. And that's essentially a way of multiplying numbers together, is adding logarithms. So you take a multiplication problem, make it into an addition problem. And that's possible by these different rules, the first two rules of logarithms. So one is that log to base a of u times v is equal to the log base a of u plus the log base a of v. Also, so that's when you add things together. When you multiply in a slide rule, you add things. When you have a division, you got the log of base a of u divided by v is the log to the base a of u minus the log to the base a of v. And whatever's in the denominator you subtract, and whatever you have in the numerator you add. So you can have u times v divided by w. We'll see that later. And then if you have something raised to a power, the last one, log base a of u to the n, that's the same as n times log base a of u. So how we talk about that here is we say you can bring the n outside the logarithm. So an exponential problem becomes a multiplication problem. And what we're going to do is we're going to use this to evaluate logarithms numerically. We're also going to expand products and quotients using these two properties. And we're also going to simplify things that have exponents. And again, this is a key thing that we're going to use in calculus. Not till the end of the first semester, but we are going to use it. So the first thing we're going to do is we're going to evaluate logarithms without a calculator using the properties of logarithms. And the way that works is, first, there are certain things that we know the logarithms of. We know that the log of a to the base a is equal to 1. We know that the log to the base a of 0 that's, well, actually, no, that's not going to work. The log to the base a of 1 equals 0. So the log of any base of 1 is 0. That's because a to the 0 power is always 1. So it doesn't matter what a is. It can be a variable. Here what we're saying is that a to the first power equals a. So those are those two things. So our first example, log base 3 of 9. So what you can do is you can rewrite 9 as 3 squared, such that, so what we're trying to do is we're trying to write this expression as 3 raised to some power, because what we can do now is, because this is now an exponent, 2 is an exponent, we can take that outside the logarithm, and then what we have left is log base 3 of 3. Well, we said log base a of a is 1, so log base 3 of 3 is 1, so the answer is 2. Okay, here's another one, log base 3 of 16. So again, if we, first that doesn't seem too good, because 3 raised to some power does not equal 16. So what can we do? So you've got, that's a good question. Yeah, I'm not even sure if that's the right problem, because I can't see any way to do it right now. But let's say if we had log base 3 of 81. If you take 81 is 3 to the 4th power. 3 times 3 is 9. Times 3 is 27 times 3. So again, you could bring the 4 outside. You'd have log base 3 of 3, which is equal to log base 3 of 3 is 1. So you get 4. If you had a log base 2 of 16, again you can rewrite 16 as 2 to the 4th power. 2 times 2 is 4, times 2 is 8, times 2 is 16. Bring that outside. Log base 2 of 2 equals 1, and you get that. Okay, here we have a root expression, but what we remember is that the nth root is the same as the number raised to the fractional exponent. So the third root is the 1/3 power. So again, once you've gotten this written in exponential form instead of in this radical form, then I can bring the 1/3 outside, the exponent outside, and I end up with log base 6 of 6, which is 1. So the answer is 1/3. This one you might be tempted to do something, but remember the domain of any logarithm function. So the domain of y equals log base a of x is 0 to infinity. And because this value x is outside the domain, then the function does not exist. Okay, so this one we have log base e of e squared, which is the same as the natural log, so you could also see this problem written as such, the natural log of e to the 5th. Again, we can apply the properties of logarithms to each one of these separately. So we bring the 2 out and the 5 out like that, using the third property of logarithms. The natural log of e is 1. Same here. So the answer is 7. Okay, so that's using the properties of logarithms to evaluate expressions. Usually trying to rewrite whatever the expression is in the argument of the logarithm as whatever the base is raised to some power. So now we're going to use the properties of logarithms to rewrite this. This is the skill that's probably the most useful in calculus. So instead of having a number here, we have the variable x. But the property of logarithm says that anything raised to a power, you can take the power outside. And you get that. So it's 4 times the log base 3 of x. Now down here, we have something, we have a division problem. So you might think that there's 2 ways to think about this. One is you could rewrite this as z to minus 3 power and then bring the negative sign outside like that. The other way that you might think of it is I'm going to use the quotient rule, which would be log base 6 of 1 minus log base 6 of z cubed. So what I've done is I've taken the numerator, separate it from the denominator, but because this is in the denominator, subtract it. But the log base 6 of 1 is 0, so the first term is 0. And then I can use the properties of logarithms to bring the 3 outside, so then I get negative 3 log base 6 of z, which is exactly what I got there, by rewriting 1 over z cubed as z to the minus 3 power. Now what we have here is we have a product. Some of them are squared and some of them are not. So when you have a multitude of products, you're going to use the product rule first. So we can't bring this squared out because the squared only applies to the x part. So what we'd have is a log base 10 of 4 plus log base 10 of x squared plus log base 10 of y. Now this is just going to be a number. It's going to be number less than between 0 and 1. And this one, though, we can go one more step because I have this exponent, which is applied just to the x. So that at that point, I can take out the exponent. And that's it. There's nothing else that we can do to further simplify that. Okay, now what we have here is we have a product and a quotient. So again, just like here we had just products, we broke it up into 3 parts. Of the 3 parts of the product, here we have 3 parts of this product quotient. And so what you do is you take the terms that are in the numerator, and those are positive contributions. And the one that's in the denominator is a negative, like that. Okay, so now we've broken it up, this product quotient thing, up into summations. And then we want to see if we can use the exponential property of logarithms. So here we rewrite the square root as x to the 1/2. And this one we just leave the same. And this one we leave the same. Okay. Now we can use the properties of this property of taking the exponential out. That's your final answer. Okay, so we got a kind of a mashup here. First thing we need to do is to rewrite the square root that's around all these things as to the 1/2 power. So all this is to the 1/2 power. So at this point we can take out the 1/2. Then this is a product of x squared times x plus 2. So we can't bring the 2 out because this squared only applies to this term. So it has to apply to the whole thing before we can bring out the exponent. So what we can do is we can take the 1/2, we'll put that outside the brackets, and then we'll break this product up into a sum because they're multiplied together. Like that. And then finally we can bring out the 2 exponent here because it's applied just to the x. So it becomes 2x plus the natural log of x plus 2. And we could multiply this out now because you've got a 1/2 times 2, so that becomes the natural log of x minus 1/2 the natural log of x plus 2. And that's your final answer. This is very similar to what we just did here. We don't have this first step because this is not to a particular exponent. But we do have a product, so we can say it's the natural log of x plus the natural log of the square root of x plus 2. And then we can rewrite this square root as a fractional exponent. And at that point, you can bring the exponent out. So you always want to take square roots, cube roots, rewrite those as fractional exponents, and then bring those outside. Okay, so that was expanding expressions. You can go the other direction and take a logarithm, series of logarithms that are added to each other, subtracted to each other, and combine them back. So it's just the opposite process of what we've been doing. So if we've got the natural log of y plus the natural log of t, what we can do is we can put those back together. So it's a product, so they're multiple. I mean, it's a sum, so we can multiply those together. So that's all there is to that one. Now here we've got a subtraction, but you always want to take constants that are out front and put them inside before you combine these things. If you remember the properties of logarithms back here says the natural log of u plus the natural log of v equals the u times v. So there's no constants in front of the natural log. So you got to get rid of those constants, and you do that by moving them inside. So the first thing that we would do is we would take the second part and we would put the product, the term out front becomes the exponent. Before we took the exponent, we moved that front. Okay, now what we can do, and notice this thing's cubed is not the natural log is cubed. X plus 1 is cubed. Now we can combine them together because this is a minus sign. What's going to happen is that the positive part goes in the numerator and the negative part goes in the denominator. And there you're done. Okay, so here we've got this multiplier that multiplies both of these, so we have to, let's just multiply it out first. So you get -4 and -4 times those two terms, just use the distributive property. Now we can move those inside the logarithm, so you get x plus 2 to the 4th and x minus 1 to x minus 2 to the 4th. So that's where the thing goes in front. And now we can combine them together. These two will be in the denominator. This will be in the numerator. So you get the natural log of x divided by x plus 2 to the 4th times x minus 2 to the 4th. Okay, here we have everything to the base 4. This 1/2 is multiplied by each one of these two terms, so let's do that first. So you get 1/2 log base 4 of x plus 1. That's the first term. 1/2 times 2 is just 1. So the second term just becomes log base 4 of x minus 1. And then the last term doesn't change because it's not being multiplied by a half. Now we're going to move the constant in front as an exponent. This one doesn't have a constant, so it just stays the same. This one it does, so it moves inside. And they're all added together. So these are all go in the numerator. So we get log base 4 of x plus 1 to the 1/2 times x minus 1 times x to the 6th power. Okay, now this is some further stuff using your calculator. So using the properties of logarithms. So this is an exponent, so we can bring that outside. Then what we have left inside, if we can rewrite 81 as some power of 3, we choose 3 because the base is 3. So that's going to be log base 3 of 3 to the 4th power. 3 times 3 is 9 times 27 times 3 is 81. Okay, now you can bring out this second one. You can do it again. So we took out the -0.2 initially. Now that we've created the exponent again, we can bring that out. And then we have log base 3 of 3. This is 1. So if you multiply those together, you get -0.8. Okay, so here we have the cube root, 4th root. So we can take e cubed to the 1/4 power. Remember the properties of exponents is you multiply these two together. So it's going to be e to the 3/4. Bring this 3/4 out. And the natural log of e is 1. So you just get 3/4. Okay, so we're going to do these together. There's two ways you can do it. You could use the properties of logarithms to combine this together. It's probably the easiest thing to do. So you've got the natural log of 5, 75 divided by 3. So I've used the quotient property of logarithms. So it's 25 And now what the heck do we do? Yeah, so let me think about this. Now this is another way of thinking. This is going to be 25 times 3, 75. So you could say that's the log of the base 5 of 25 plus log to the base 5 of 3 minus log to the base 5 of 3. So I've broken this up, and these cancel out. So I get the log to the base 5 of 25, but log 25 is 5 squared. So you bring 2 out, so you get log to the base 5 of 5, which is 1. So you get 2 times 1, which is 2. Okay, so why didn't this one work so well? I don't know. Let me just think about this for a second. Natural log of 25 divided by the natural log of 3. I'm using the change of base formula. 75 divided by 3 is 25. Anyway, let's just try this. Oh, I know what it is. When I wrote this down, I changed that to a 3. That should be 5. So there you've got log to the base 5 of 5 squared. Bring the 2 out. You got log to the base 5 of 5, which is 1. So that was my problem. When I went from here to here, I wrote down the wrong base. Okay, I think this is the last example in this section. How many integers between 1 and 20 can be the natural log? Can be approximated by using these 3 known things. So, obviously we know what the natural log of 2 is, because we're given that. Same with the natural log of 3. The natural log of 4, well, that's going to be the natural log of 2 squared. So that's going to be 2 times the natural log of 2. So I have the natural log of 2, so that one we can do. The natural log of 5 we already have, 1.6094. The natural log of 6, so that's the natural log of 3 times 2, which is the natural log of 3 plus the natural log of 2. And I have both of those, so I can do that one. Natural log of 7 I can't do anything with. Natural log of 8 is going to be equal to the natural log of 2 cubed. Bring the 3 out, so it's going to be 3 times the natural log of 2. So I know how to do that. The natural log of 9 is the natural log of 3 squared, which is 2 times the natural log of 3. So I can do that one. Natural log of 10 is going to be the natural log of 2 times 5, which is the natural log of 2 plus the natural log of 5. So I can do that one. I can't do 11. 12 is going to be the natural log of 4 plus the natural log of 3. 12 is 4 times 3, and I already have 4 and 3, so I can do that. 13 I can't do. 14, no. 15, yeah, I think I do 15. So that's the natural log of 3 times 5, which is the natural log of 3 plus the natural log of 5, so I can do that one. 16, that's 2 to the 4th power, so that's 4 times the natural log of 2, so I can do that one. 17 I can't do. 18 is 2 times 9, which which is the natural log of 2 plus the natural log of 9. I already have those. 19 I can't do. And then 20 is 4 times 5, so it's the natural log of 4 plus the natural log of 5, which I already have. So basically, knowing the natural log is 2, 3, and 5, I can do 4, 6, 8, 9, 10, 12, 15, 16, 18. So it's just the prime numbers that I can't do. And there's some homework.